now let's go to the next topic of today's lecture is two-sample testing for mean. Two-sample testing for mean. So in two-sample testing for mean, we are interested in such testing problem. So H now is formulated as mu1 minus mu2 equals mu0. So remember, let me recall the model assumption. Normal model or non-normal model and 1 and 2 large, both large. Our hypothesis testing is like follows. And we would like to we utilize the following test statistic. The test statistic is T test statistic. It is capital X bar minus Y bar minus mu0 mu null divided by So before introducing the test statistic, let's first see an introductory quantity. So this thing, X bar minus Y bar minus mu0 divided by square root of variance for X bar minus Y bar. So pretend we know the population variance sigma 1 square and sigma 2 square. What is variance of X bar minus Y bar? So variance of X bar minus Y bar is just the variance of linear combination of random variables. This is quite straightforward because X bar and Y bar are independent, which is right this way. There is no covariance. Sigma 1 square divided by n plus sigma 2 square divided by n2. So, which means in our testing problem we don't know. So, suppose this is known, we can calculate this quantity. But actually, in this setting, we are testing about. We assume that. Okay. So this as the first. So if sigma square and sigma 2 square is known, then what this quantity is, let's plug in. So X bar Y bar itself follow mu1 minus mu2, which is mu0, and sigma 1 squared divided by n1 plus sigma 2 squared divided by n2. So then this testing is just one. So let's give a remark. The remark is when sigma square and sigma square is known, then two-sample testing for mean is essentially one-sample mean testing, and we have known how to perform one-sample mean testing. which has been tackled in the first lecture video. Okay, so 1 sigma square, 1 square, sigma 2 square are unknown. We have two cases. Case 1, sigma square not equal to sigma 2 square, unknown. What is the test statistic for such to perform such hypothesis testing? So we use T test statistic. It defined as follows: capital X bar minus capital Y bar minus mu 0 divided by square root of sample variance of the first sample divided by n1 and sample variance of the second sample divided by n2. And remember this as a fact. It follows T with degree of freedom of minimum of n1, n2, minus 1. So this T distribution with degree of freedom of the minimum of n1, n2, minus 1. And let's see the p-value, how to compute p-value. The p-value is probability of absolute value of capital T greater than small x bar minus small y bar minus mu 0 absolute value divided by square root of small s1 square divided by n1 plus small s2 square divided by n2. So this is the p-value. For decision rule, is probability of absolute value of capital T greater than some constant equal, and we set it as alpha. This is our way to determine the constant C. We have done this for two-sided. We have seen such form before. And for power, one minus beta is probability of absolute value of capital T plus mu star minus mu 0 divided by square root of capital S1 square divided by n1 capital S2 square divided by n2. Absolute value greater than T minimum of n1 n2 minus 1 alpha over 2. So this is the power function. 1 sigma square unknown but unequal. So let's see the second case. Sigma square equals sigma 2 square, both unknown. How to compute which test statistic can be utilized. So let's see the test statistic. Test statistic is T tilde x bar minus y bar minus mu 0 divided by square root of capital S put 1 over n1 plus 1 over n2. And this following T n1 plus minus 2. So what is capital S squared put? Capital S squared put is defined as n1 minus 1 capital S1 squared plus n2 minus 1 capital S2 squared divided by n1 plus n2 minus 2. So how to utilize this test statistic to perform hypothesis testing? So for p-value is probability of capital T tilde, absolute value of this random variable following this test statistic greater than absolute value of small x bar minus small y bar minus mu 0, absolute value divided by square root of small s put times 1 over n1 plus 1 over n2. This probability is the p-value. And for decision rule, it is also the constant c can be found in this way. And for power, 1 minus beta equals, so we need to specify mu1 minus mu2 equals mu star, not equal mu 0. So the power function is like this, absolute value T tilde plus mu star minus mu 0 divided by square root of capital S put 1 over n1 plus 1 over n2, absolute value greater than t, n1 minus plus n2, n1 plus n2 minus 2 over 2. This probability is the power to this problem. Okay, let's do a quick review for this testing problem. So the second topic of today's lecture is to perform hypothesis testing about two-sample mean. So the hypothesis we're interested in testing is like this: mu1 minus mu2 equals mu 0, and alternative hypothesis mu1 minus mu2 not equal mu 0. And our model assumption is normal model or non-normal model n1 and 2 both large. And we first observe that if sigma 1 sigma 2 square is known, then we can compute this quantity. And we also notice that x bar minus y bar itself is again in normal. So we have this remark: when sigma 1 sigma 2 square are known, this two-sample mean testing reduces to one-sample mean testing, which has been tackled in the first lecture video. And when sigma 1 square, sigma 2 square are unknown, we have two cases. The first case is sigma 1 square not equal to sigma 2 square, unknown. We use this test statistic capital T following T distribution with the degree of freedom of minimum of n1 and 2 minus 1. And we introduced how to compute p-value in this way, decision rule in this way, power in this way. And the second scenario is sigma 1 equals sigma 2 square, but also unknown. The test statistic is T tilde x bar minus y bar minus mu null divided by square root of s post square times 1 over n1 plus 1 over n2, following T distribution with the degree of freedom n1 plus n2 minus 2. And S put is defined in the following way, and we introduce how to compute p-value in this case, decision rule, and power. Okay, so finally, let's see an example to apply two-sample mean testing. Example. So suppose the first sample x1 kept x1 all the way to kept xn1 random variable following Bernoulli p1, and for the second sample kept y1 all the way to kept yn2 random sample following Bernoulli with probability p2, and we are interested in testing h now p1 minus p2 equals 0, and h alternative p1 minus p2 not equal to 0. And why do I say that it is a two-sample mean testing? Let's recall. So expectation of xi is p, variance of xi is p1 times 1 minus p1, and expectation of yi is p2, and variance of y is p2 times 1 minus p2. So this hypothesis tests p1 and p2. So since p1 and p2 are mean of those random variables, so this is a two-sample mean testing. And this is the case 2. And the h null, y case 2, and the h null, which is p1 equals p2. Then we know variance of xi equals variance of yi. So variance are equal, which means sigma 1 squared equals sigma 2 squared. In this case, sigma 1 squared is p1 times 1 minus p1. Sigma 2 squared is p2 minus 1 times 1 minus p2. So this second case, since p1 p2 we don't know what p1 p2 really is, but we know that and h now they are equal. So this is case 2. What is case 2? Let's take a quick review. So case 2 is sigma 1 equals sigma 2 squared, unknown. The test statistic is t tilde. Let's see how to compute t tilde in this case. So t tilde is x bar minus y bar minus mu null divided by square root of capital S put 1 over n1 plus 1 over n2. This is what t tilde is. Okay, let me give you some real value. So in this example, n1 is 6124, n2 is 5512, and small x bar is 0.4, small y bar is 0.37. So this is case 2, and for model aspect, this is non-normal model, and 1 and 2 both large. So the model assumption, it satisfies the model assumption, non-normal model, and 1 and 2 both large. So we can compute this test statistic. So in this case, x bar is we denote it as p1 hat because it is defined 1 over n1 summation I from 1 to n1 xi, and for y bar we denote it as p2 hat 1 over n2 I from 1 to n2 yi. This is for x bar, y bar. And for the hypothesis testing, so the mu0, mu1 minus mu2, here mu1 is p1, mu1 minus mu2 in h now, so mu1 here is p1, mu2 here is p2, and in h now p1 minus p2 is 0, which means mu now itself is 0, 0. And remember as a fact that output its definition is as n1 minus 1 capital S1 squared times plus n2 minus 1 plus 2 squared divided by n1 plus n2 minus 2. And we, in this case, remember, just remember, output is n1 x bar plus n2 y bar divided by n1 plus n2 times 1 minus this ratio times 1 minus this ratio n1 x bar plus n2 y bar divided by n1 plus n2. So remember in this case, in Bernoulli case, you don't need to calculate. You need to calculate use its original definition. In this way, there is shortcut, output shortcut, which means these two are equal in Bernoulli case. These two are only equal in Bernoulli case. This is shortcut. This is shortcut to compute n-squared put in Bernoulli case. Okay, the third video is finished. Let's meet again in the fourth video and fifth video. See you next time.